that, this one is from the Hooke's law. If you were to cut that, that means the spring has got that force that's exerted. Right? That's why the spring is under tension. You want to find out what is that spring force. So we're going to find out spring force. The Hooke's law says that that force is equal to kx. But in our case, this x over here refers to the static displacement because x refers to how much it has moved, right, along that force. So static displacement. So we can go on and fill in all the rest of it. These are the forces. F is equal to K sigma st. Right? The st there refers to static. So we can take one of the force, maybe this force over here. This force, we can also figure it out why is it equal to K sigma st by taking the length plus static displacement and then minus the natural length. Right? So what am I doing here? This is the length plus static displacement. I just want to find out what's the difference. So take that whole length minus the natural length. So what I'll get will be K sigma static. So those are the forces that's acting around this mass. Let's have a look at the case of the disturbed condition. We have that mass, and in this dynamic condition or disturbed condition, you'll find that the mass is moving down with an acceleration. Why acceleration? Because then it's dynamic condition. Right? This mass got to move in order to be qualified to be called as a dynamic movement. So when it moves down, then there will be some form of acceleration. So that acceleration, sometimes in some textbook is written with a symbol A for acceleration. But A sometimes is also used for measurement of length, like length A, length B. So in dynamics, I think you get to see more of this x dot dot. And this is tied to time. So at different point of time, the acceleration may be different. So that x dot dot is the second differential of the length that is going downward. So you would still experience mg right from the mass. And what we're interested in would be the four forces. The four forces. 1, 2, 3, 4. So the forces in this case for the dynamic condition will be equal to K, and we'll be taking this full length here under the dynamic condition. Is Lm plus sigma st plus x minus away the natural length. That's the total amount that it extended, right? So you see that is equal to K static displacement plus the amount that you pull it down. Okay. So now I can have all this filled in. This will be K static plus x displacement, K static plus x displacement, and all of that. Now, this st over there, at some point of time, I may drop it because it takes a lot to write st continuously. In previous year, there wasn't this st, but because there's a new lecturer this year, and he introduced the st. same as what you can find in the notes, but sometimes in the slides, you will not see ST, just this sigma symbol. I also noticed that some students don't understand how to write symbols, the Greek symbol. So sigma is written in this way. It's not this way. I think some of your handwriting, when I see it in the exam, you seem to learn it somewhere in your earlier education, and then it became sometimes that way. Yeah, that's sigma. But no, sigma is written in this way. If you want to see me how I write that way. Okay. Yeah, sometimes it's also called delta. Usually we use triangle. So it's a mathematical system.
No, because the thing is, we got actually, the mic can just do it because it's not problem because it's very big.
I think I said wrong. This one is sigma, and this one is delta. So this is a small letter for delta. This is a capital letter for delta.
The whole system.
So this one is the delta.
I can mount it to my bed.
So the next step that we want to do is that we're interested in this part. So I'm going to use a different color. We're interested in these two parts over here. So let's start with the static condition. For the static condition, you have that figure over there. I'll sketch it out again. You have the mass, datum x. That mass has got mg, and then you have a force that's acting upward. That force is equal to k delta st. So if we consider this mass, consider the forces around the mass, that means what we do is to sum up the forces along the x-axis, and since it's in static condition, this will be equal to 0. Right. So let's sum up all the forces. This symbol over here represents summing up. So if I sum up all the forces, if my datum says that x direction is downward, so mg will be a positive value. And this force is going upward, k delta st is upward, so it's minus k delta st. The whole thing equal to 0. That's summing up all the forces along the x-axis. So this one will stay. Later on, we'll make use of that. And then you have the disturbed condition. Under the disturbed condition, this is where you have motion. Right? Because what you do is that you pull down that mass, and then it's up to be released for oscillations. So I'll sketch that figure again. So if you again consider the mass m, that is this case, you have mg as well, and you have the force that's equal to k delta st plus x. So what we'll do for this case is that there's acceleration, x dot dot downward. So we'll sum up all the forces, and in this case, it's not a static condition, it's not equal to 0, but it will be equal to ma, right? It's the same as F is equal to ma, but we don't write acceleration a in dynamics, we write x dot dot for acceleration. So let's sum up all the forces again. We have this one is going downward, again is a positive value, mg. And then this force is acting upward, is against our convention, so minus k delta st plus x. The whole thing equal to mx dot dot. So I can expand this out, mg minus k delta st plus this minus as well, minus kx over mx dot dot. So if you compare these two sets of equations, you'll find that this term over here is actually equal to 0, right? Because mg minus k delta st is equal to 0, so it's equal to 0. So on the left, you gotta move everything to one side. It will be mx dot dot plus kx equal to 0. So this equation over here, I'll call it equation A. Now there's something about equation A that I want to talk about. If you notice carefully, we started with this G over here, or that system, right? The two systems that we can see up there. We started with G, and eventually it comes to this set of equation that does not contain G anymore. What that means is that you'll get this kind of response by just perturbing your spring with a loaded mass, just perturb it, let it oscillate. No matter where you are on planet Earth or Moon, this motion is independent of gravitational pull, G, because G is not found in this equation over here. So this is the one. This equation is independent of gravity, G, because you cannot find it there. If you're wondering, then where is G suddenly disappeared? Well, G disappeared because your x is measured from the static condition. The static condition, if you just see what we have just now, this is a static condition. So if we measure x after we perturb it down, then that gravitational pull is actually not relevant to us anymore. As shown in this calculation, it will just cancel off. So that static delta part would also disappear under the dynamic condition. The second insight to this equation, this motion is actually unforced. Some of you may be wondering, why is it unforced? I thought we just heard that I kind of pull it down and then release it and then oscillate. I thought that pulling that part, isn't that a force that you're pulling? But I consider time to start, not at the time when I pull it down. No. I consider time to start after I pull it down, and when I'm about to release, then time will start. So anything before that, I'm not really interested. So if time starts from 0 when I release, after I pull it down and release, then this system actually don't have any external force that's acting on it. You may be thinking there's a friction, there's a friction. Oh yes, there's damping. But now we're considering the case of undamped. So in vacuum where there's no friction. Yeah. You may be thinking, wouldn't there be the force that's due to the mass? Yes, the force due to the mass is actually always there, but there's no external force acting on it upon release of that mass. So this system is what we call free vibration. So you're going to hear this a lot. Free vibration, or sometimes in certain textbook it's called free response. The third insight, it will have two initial conditions. And initial conditions here refer to when time is at 0 seconds, that x, this x over here, and if you have forgotten, the x that I'm referring comes from this x, this dynamic deflection. That x at time equal to 0 because we pull it down by certain displacement, certain downward displacement. So at time equal to 0, you must have certain value I call x naught. In your set of notes, you can see that it's represented by a capital letter X. So later on I'll talk a little bit about that too. But it's just different ways of representing. You can use either one. But I find that using small letters is actually more intuitive. Yeah. There's also another thing. At time equal to 0 seconds, the x dot, which is velocity, when you pull down that mass, pull it down, at time equal to 0, that velocity will be equal to 0. So these are the two initial conditions. Yeah. Later on, we'll make use of that. Now, sometimes you also get to see that these two terms over here, in mathematics expression, is compressed into one that is written in x at time equal to 0 equal to x naught. Sometimes written in that way to represent these two. So the same goes for this case. Velocity at time equal to 0 equal to 0. Yeah. Written in a very compact way. So there is this assumption that when we pull down the mass, that at that moment before release, the velocity is equal to 0. This is, or this case, this system. At some point later on, we'll see one example where we don't start with a 0 velocity. So for those cases, we'll be discussing that. But in this case, I'm starting with a 0 velocity just before I release that mass. So I'll just write it here. It's with an assumption that at time equal to 0, the system is stationary. That means not moving at all. It's an assumption. There will be some other cases where the system will be moving and its initial velocity may not be 0. So we can have a look at those. The fourth insight that I want to give you is that this kind of expression actually has a special name to it. It's called homogeneous second order linear differential equation. This expression over here. So you can go home tonight and say to your parents, hey mom, you know what I learned today? I learned homogeneous second order linear differential equation. And your mom will look at you, son, daughter, I think I sent you to the right place. Besides this mathematical wording, we see how we can go about solving it. So this is where it breaks up. This is where the two lecturers in Glasgow, they have different opinions in solving homogeneous second order linear differential equation. You have two methods. So I introduce these two methods to you. In the exam, you can use either method. Yep. Last year, we actually used only one method because only one person teaching. This year, they split it up. So the first method. The first method is actually called the Euler's method. It's actually also covered in your set of notes. Yeah? You would have learned before in your earlier education, and actually your online bridging courses also try to expose you to this mathematics, but unfortunately some of you choose not to attend. So no choice. Then you have to pick it up and hear by yourself now. We try to reach you, but you choose not to attend the online Math Quest. So the solution for this kind of equation, the solution for A, actually we know that it must be a quasi-sinusoidal. What that means is that this x expression must follow this kind of general form. A sine omega nt plus b cos omega nt. This omega n over there is our natural frequency. Later on, I'll talk a little bit about that. That n over there stands for natural. Omega is frequency. Yeah. So some of you may be wondering, how do you know? How do you know this x actually has this general form? I know. Because I work on this a lot of times. But you'll be wondering, but I don't know. Yeah, it's fair, yes. In your set of notes, they actually try to work backwards to prove you actually that assumption is correct. Alright, so let's see if we have time, maybe we'll just go through a little bit of that. But if we are okay with this assumption, then I can go ahead and differentiate it. And by the way, in your set of data sheets, there's no differentiation of cosine and sine, either kind of table or formula. That is in earlier education. Now you're an expert. No equation. But then some of you will get very worried. Then who's going to help me? I will help you, yes, by giving you a lot of examples. So many examples that once you see, differentiate sine omega t is the same, is equal to omega cos omega t. It will come to you. We'll take this as one example. Differentiate this. If you were to differentiate this, that A would stay. Do you recall differentiating sine will give you? Cosine. So it's cosine omega nt. So in this case, this is not sine theta. This is sine omega nt. So if you differentiate sine omega nt, you still need to differentiate the inside of this with respect to t. So differentiating omega n t will give you omega n. Right? So you have omega n over here. How about differentiating this part over here, b cos omega nt. Differentiating cos will give you
Minus cosine, minus sine.
minus sine. So minus sine omega nt, and then you differentiate this inside, you get omega n. Okay. Now, if all this is very new to you, it's time. So if I differentiate one more time, and why do I need that? Because I have an x dot dot over here. Later on, I want to fill it in. So differentiate this one more time. So differentiating cosine will give me minus sine omega nt. And then differentiating omega nt again, you get omega n squared. So minus omega n squared a sine omega nt. This part here, differentiating sine will give you cosine omega nt, and then differentiating omega nt again, you get omega n squared, and then that sine remains. This differentiating sine, you get cosine. Differentiating cosine, you get minus sine. So now we can substitute these expressions into A. Okay. So if I were to do that, then I'll get, okay, bring it down a little. Equation A is this, so it will be m x dot dot minus omega n squared a sine omega n t minus omega n squared d plus omega n t plus kx plus k, and x will be a sine omega n t plus b cosine omega n t equal to 0. So if you have that, after you have that, what we're going to do is to apply the initial condition. The initial condition says that, sorry, not initial conditions. What we want to apply is when that angle, that's omega n, is small. So just to break up a little, so if sine theta is small, then sine theta can be approximately equal to, do you remember? Theta, right? And cosine theta approximately equal to 1. Okay. That is if theta is small. If you don't believe, you can use a calculator. Put a very small value, sine theta, and then you'll find that sine theta close to theta. Put a small value to cosine theta over here, and you'll find that it's actually very close to 1. So if that's the case, that means this term over here, the sine part approaches omega nt. This term here approaches 1. This one, omega nt. This one approaches 1. So I'll write it down everything. M minus omega n squared a omega nt, and then minus omega n squared b plus k a omega nt plus b equal to 0. So I'll just do a little bit of simplification. Minus m a omega n squared and omega n t minus m omega n squared t and plus ka omega n t plus kt equal to 0.
Check my confused.
And what we do next is to bring out all this
Wn square out.
omega n. Right? So I will have this omega n squared, and then bring this one over to the right hand side. So I have minus ka omega nt minus kb. So finally, my omega n squared, I can express it in that way, is ka omega nt plus kb. Or maybe I'll just bring that k out since it's common factor. It's 2k. Divide by, I'll bring that minus m out. So I have a omega nt plus b. So you can see these two terms will cancel. So omega n is equal to square root k over m.
Oh, wow. Impressed.
So your lecture notes actually go ahead and try to solve what using the S domain, but I'll talk a little bit more about S domain when we come to the other method. So this is a natural frequency expression for that setup that you saw just now. Just a simple spring per term, and then it has a certain natural frequency that relates to the mass and relates to the spring constant in this way. So if I want to solve for what is the expression for the x value, then what I need to do is to apply these initial conditions. So there are two initial conditions. If I write them out again, x naught is equal to x at time 0 is equal to x naught. And the velocity at time 0 is equal to 0. So substituting these two initial equations into the following expression, this following expression, this one, maybe I'll call it B. So substituting these initial conditions into B. So what I have is that x will become a sine omega n t plus b cos omega n t. And this sine term over here would become 0. No, not yet. Then I need to let this whole thing here, x at time equal to 0, will be equal to x naught. So in your notes, x naught is written as capital letter X. It's just different way to write it. So you can adopt either convention. So if sine 0, if this is sine 0, then this whole thing will become 0. Cosine 0, you get this whole thing equal to 1. Yeah. So what that means is that, therefore, this whole thing equal to 0. That means your B is equal to x naught. This is cosine is equal to 1. So if you substitute this condition into C, right, C above, so substituting into C, that means your x dot equal to A omega n cosine omega n t and minus B omega n sine omega n t equal to 0. Right? The velocity is equal to 0. And this happens at time equal to 0. Right? So what that means is that this cosine will be equal to 1, this sine term will be equal to 0. Right? So what you're going to have is that this A omega n will be equal to 0 and A is equal to 0. After applying these initial conditions, hence x has an expression. This A now is equal to 0, so you don't have that. B is actually x naught. And then cosine omega n t. So this is after you found out what are A and B values, okay, using the initial condition. Then you put it back into that general equation. The general equation of x is equal to A sine omega n t plus B cosine omega n t. This is a general equation. We found out A is equal to 0 and B is equal to x naught by putting in the initial conditions. So this is an expression that if I were to pull down that spring and let it oscillate freely, what is the equation for this oscillation? It's written over here. Xt is equal to x naught cosine omega n t. That's the expression for that oscillation. Yes, ma'am.
For the whole.
Why this expression?
Whole.
That's because of this.
Hey, what are you thinking?
So we're using this x dot condition with time equal to 0. So time equal to 0. Time equal to 0. So sine of 0, you get 0. Cosine of 0,
Being in
you
the
get
fix their head, settle swap. Whatever strap you want, chest strap, head strap. I got chest strap, I got head strap, I got shoulder strap. What strap you want? Yeah, this one is the GoPro one. The shoulder strap is 6 year one, then the chest strap, then I got arm strap, then I got head strap. Chest strap.
second method.
Wow.
This is alternative method. So just now, this method is called Euler's method. Okay. Now we have a second method.
Not for the two bloody head, right?
The second method is Laplace transform.
No thanks. My lah.
And how about let's go for a quick break and then we'll be back 5 minutes later and then we'll enjoy this.
Okay, pause.